use of differential equations for solving Newton's second law come when we look at oscillations. So once again, we're going to be looking at Newton's second law, which is where force is equal to mass times acceleration. And in this setup, we're going to use x to denote the dependent variable. So it'll be the horizontal position at time t with velocity x prime and acceleration x double prime. Only this time, instead of something going up and down, we're going to be looking at the oscillation of some object as it bounces back and forth. And so suppose we've got some mass. So there's mass m right here. It's connected by this spring to some wall. The spring has a spring constant of k from Hooke's law. So that's describing the force that it pushes back towards equilibrium when displaced from the equilibrium position. So here, this is a position where the mass is actually at equilibrium. The two little lines are matched up. So horizontal position here is x equals 0. And then there's also some damping provided by the coefficient of friction. So C for coefficient of friction. And then there may also be some external force, so pushing on the system from something outside. So over here, we see what it looks like when the mass is extended some positive direction, so moved to the right from equilibrium. And in this case, the spring constant is going to be pushing back. It's a restorative force pushing back towards equilibrium proportional to the distance that it's been stretched. So let's see. So the way Newton's law works, we just need to sum up the forces. So mx double prime is going to be, now what are the forces on this spring? Well, we have the restorative force, k times x, coming from the spring, and that's pushing back towards equilibrium, so it's in the opposite direction of motion, so it comes with a minus sign. And then we also have the drag force here from the coefficient of friction, so that's proportional to velocity. And again, it's a force that's opposite the direction of motion because it's slowing you down, so that comes with a minus sign. And then there's going to be some external forcing function, and who knows what that's doing. So in general, we have an equation that looks like mx double prime plus cx prime plus kx equals f. And so you can see I've grouped it here so that all of the instances of the dependent variable appear on the left, and all the stuff that doesn't include the dependent variable is over here on the right. And although it is beyond our ability at present, we will see that the solutions to this equation are of the form e to the at cosine bt or e to the at sine bt. And it turns out, actually, that the a here, so the rate of decrease, is minus c over 2m, and the b is given by c squared minus 4km square rooted all over 2m. And if these look familiar, it's because these are the same roots that you would get trying to solve this equation right here, as if it were a quadratic equation in x. So in other words, where the roots are, let's see, minus c plus or minus square root c squared minus 4km over 2m. Actually, that's not r. That's going to be something about the frequency of our oscillation. The key point is that this is going to look like something that is, let's see, it's going to have a decaying amplitude, so something like this. So this is the e to the minus c over 2mt, and there'll be some corresponding negative part to that as well. And then when we multiply this against, say, this cosine bt term right here, then we'll have some, so here's some, oh wow, this is not going to be my best cosine ever, but maybe not too bad. So when I multiply those two functions together, so again, this one here, this was cosine bt, then the resulting function is going to be something, well, if If you multiply by 0, it's still going to be equal to 0, so it'll still pass through exactly these same nodes right here. But now, multiplying by this smaller amplitude will bring the cosine to be squashed something like that. So it'll be, let's see. Yeah, there we go. Okay, so we have some decaying oscillation, bounces down and then up and then down and then up, but it's asymptotic to equilibrium.